Yeah, yes, sir. Live started, sir. Can start, sir.
Has it started? On YouTube, I still see it says waiting.
No, started, sir.
Okay, right. Thank you. So I welcome you to this live session 2, which is from weeks 7 to 9. We'll be covering the topics on kinematics, which can be a tricky topic sometimes. So it's good to have some clarification. So this is going to be mostly based on the questions people had raised in the course chat group. So we have compiled those questions, and we have also compiled a list of topics to discuss so that it clarifies those queries. Although we've answered them, most of them on the chat, but we thought of discussing them in this live session today. Right. So what I'll do is I will open the lecture notes and quickly browse through the topics on kinematics, and then I'll pause and discuss in detail wherever there were queries. So let me share my screen. So lecture number 31, that starts from, um, right, still opening. So lecture number 31 starts the topic of kinematics. So in this lecture, we talked about the fundamentals. Sorry, things are still opening up, so it just keeps changing the screen. Right, so hopefully it's done now. So we started the discussion on kinematics with the idea of configurations, where we said that configuration basically denotes any particular relative positioning of the different points in a body. And remember, in continuum mechanics, we are mostly interested in the relative position of points, not in the absolute position of points. So translation is not important for us, and you will see that when we define the quantities in kinematics, we get rid of the translation because that's not interesting in this subject of continuum mechanics. So we talk about configurations, and through that, I mean, initially the idea is developed through positions of particles, which we call material particles. So if I mean, that's usually an intuitive concept because you track a point in a body. I mean, if it's a solid particle, you sort of, let's color it. Um, in fact, in many research areas, people make these particles as radioactive and then track it in some sort of radioactive particle tracing mechanism using some. In fluid mechanics, also, we make sometimes particles radioactive, and we use techniques like PEPT to track them. So it's this idea is very intuitive, and through that we discuss the um, deformation. So if you go from an undeformed configuration to deformed configuration, so we get this deformation function chi, or the mapping function, where if you feed in the particle id, or its whatever the label of the particle is, it gives you the position in the deformed configuration or even any configuration. And we can also define an inverse mapping. So if I give you a position in the body, you can tell me what particle is sitting there. So this is just a concept that is developed, and then through that we discuss the idea of deformation. When deformation happens, the particle relatively moves. If you fix one of the particles, and then you will see that the other particles are moving with respect to that. So the whole idea is to be able to develop the idea of motion. So we talked about initial and reference configuration, which is sort of mostly overlapping, where we say that t equal to 0 is our initial configuration, where we'll be talking, all deformations will be discussed in reference to that. Although technically we say reference configuration is the configuration from which we take all the deformations, or the displacements. Now, reference configuration may not be realized. It can be an imaginary configuration. It's just for reference of um, taking deformation or displacements. And remember, initial configuration is at t equal to 0, but in most cases we end up taking the initial as the reference, but that is not a strict requirement. Right, so then we moved on further to talk about material coordinates, because when we talk about the description of motion, we don't stay with particle IDs anymore. In fact, one of you had a question that why do we even talk about the idea of configurations? I mean, why do we talk about the idea of particle IDs if that is not required? So that is just for building the intuition. Ultimately, the aim is to have a Lagrangian description of motion to start with, and then we can also develop an Eulerian description of motion in terms of the spatial coordinates. Right. So as you can see here, we have this position of particle at any later time t, which is the spatial coordinate, can be written in terms of its material coordinate, or the Lagrangian coordinate, and the time t. So basically what we are saying is that if you know the position of a particle in the reference configuration, uh, that sort of denotes the particle that you're talking about, and I give you a time, you can tell me where exactly that particle is sitting at a later time. So this is that chi function that is important for uh, deformation or sequence of deformations in this case, because you have a time as well. And through this, we discuss the idea of the trajectory of a particle. Now, remember, when we say trajectory, what we are doing is we're tracking the particle in time. So, if I fix capital X, that basically fixes a particle, right? So, capital X is unique for each particle. So, once you fix capital X, that basically denotes a particle, and then if you track these small x's for that particle on a later time, that gives you a trajectory of the particle. Now, if you want to find the velocity of the particle, all you have to do is, if you think from first principles, then you have to find the derivative of the position of the particle. So, as the position of the particle, that is small x, changes, you take the derivative of that. Now, another confusion that arises here is that why don't we take capital X here? Well, capital X is not a function of time, it is actually unique. So, if you are talking about a particle P here, then for particle capital P, there's only one capital X, because that's the position of particle P in the reference configuration. So time derivative of capital X for particle P will be 0, because that never changes. That by definition is unique. So velocity is the time derivative of small x, and we represent the small x in terms of capital X and t. That's a Lagrangian description of motion. So that allows us to write the velocity field if we keep it general in capital X. So this can be a bit confusing, but always remember that the definitions of small x and capital X, and they'll make sense. And acceleration by definition is the time derivative of the velocity field. Now, if things are expressed in the Lagrangian description, there's no confusion, because we're just tracking the particle where you have substituted the capital X for a particle, so that denotes a unique particle. So this is just tracking the time rate change of the velocity or the position of the particle. Right. So next is the idea of an inverse mapping and then Lagrangian and Eulerian descriptions. So this is extremely important because I'll skip this part and then I'll move on to the Lagrangian description, which is basically describing the quantities in terms of capital X's and T. So things will change with time. That is the reason we study continuum mechanics. Although in many cases we only talk about one deformed configuration, but you will, in most general case, you will see that things will evolve with time. So things are a function of time. But the question is, what about the position? Now, the most intuitive thing in terms, especially in terms of solid mechanics, although we want to keep the discussion general, you think of tracking material particles. So you take a particle, let's say capital A here, and you track the density. I mean, that's a small material particle, which you can sort of color it to start with. So you track the density of that material particle over time. Could be anything else as well. So what that means is that you're tracking that particular material particle's properties. Could be density, could be temperature, could be velocity, could be pressure, could be anything. In fluids, you can think of, when you have a fluid initially, you take some fluid area and you sort of put an ink in it at t equal to 0. So you put a blob of ink, and then as the fluid flows or the flow field evolves, you will see that a blob of ink making following a track. So that sort of will be the deformation or the rate of deformation of that blob of material particle to start with. But again, as I said, that we want to keep this discussion general. So that's the Lagrangian description. In many cases, that's very intuitive because we think of one particle sitting at a particular position at t equal to 0, or what we call the reference configuration as the initial configuration. And then we see how it's evolving in terms of the properties of the particle. Other description is the Eulerian description, where we say that I don't care about the material particle. I care about a physical point in space or a small volume around a physical point in space. Let's say looking at you're sitting at the bank of a river and you're tracking. You're looking at some spatial area and you see how the flow is changing with time. You may see some froth developing and then it vanishes and so on. So what you're seeing is that you're saying some properties, physical properties, which are changing with time at a particular position in space. So if that is what is of interest to us, then we use an Eulerian description. Now that's very intuitive, but when we start doing things mathematically, things become a little more complex because what's happening in a particular volume in space is due to different particles crossing through that volume over time. So it's different particles coming in with different properties over time. So one has to take care of that because the physical laws of motion usually are written for particles. When you say force equals mass times acceleration, that's a mass we're talking about. So if you want to write that Newton's law, second law in terms of Eulerian description in a physical volume, then it becomes a little more complicated. And this is where we bring in the idea of material derivative, which we introduced in lecture number 34, I guess. So here we define that if I mean an observer is attached to a material particle, sort of you're tracking a material particle, then how does a property theta could be any property, it changes with time. So that's called the material derivative. So if it's a Lagrangian description of motion, it's very intuitive. But if it's an Eulerian description of motion, then we get through the chain rule, we see that we get this material derivative, which is a local rate of change and a convective rate of change. And we explained that through this swimming pool example to give you some motivation. And we also mathematically showed that the Eulerian or the material derivative that we have shown is indeed um, the derivative if you're sitting on a particle and measuring the change of property with time. So this is the reason we write this del, the local and Eulerian rate of change, as actually a material derivative. So material derivative has a particular meaning, which means that you are measuring things by sitting on a particle, right? And although today's discussion will be kept around kinematics, because there were lots of questions on kinematics, but when we move to the discussion on balance laws, we will see that this is where we start applying these ideas, because balance laws are applicable to material description, although we are interested to describe things in a Eulerian way, so we can bring in the idea of material derivative. Right, so this was a tutorial. There was a mistake in I think this problem where we had to find the acceleration. One of these problems. This one. So we had missed one term, so that I had checked and discussed in the group chat. So if for this problem number 3, you did notice that a term is missing, then you were right. That term was missing in the expression for acceleration, and this should be written correctly. So this a couple of you had pointed out in the chat, thankfully, and then we will ensure that these are corrected in the videos in the next iteration for next term. But please excuse us for this time for this error. Right. So this was some fundamentals of the ideas on kinematics, but then we move on to the actual ideas on deformation and displacements. So let me quickly check if there's any question. There's a question that assume that we have a velocity field in the Eulerian description and use the transport theorem to obtain acceleration. So what I think is you're saying that you use the material derivative uh, to calculate the acceleration in the Eulerian form in terms of velocity. And then the thing is that you also had a chi function, which basically allows you to go from uh, capital X to small x, and you had the velocity in the Lagrangian description, and you found the acceleration in the Lagrangian description. The question is, can we use the chi function and the acceleration in the Lagrangian form to get the acceleration in the Eulerian? You can. In fact, this is done in many cases where we find the velocity and acceleration in the Lagrangian forms. And then if you want things in the Eulerian form, then you use the chi function to do a coordinate transformation from capital X to small x. In fact, I think in some of the problems you may already have done that. They will not be different. They will be the same. That's the whole idea, that they should not be different. So please check it out in problems, and they should turn out to be the same. So if you start with the Eulerian description, take material derivative, or you'd start with Lagrangian description and use the chi function in the end, they should turn out to be the same. In fact, the textbook we are following, Mace and Mace, has quite a few problems in the kinematics chapter where they ask you this kind of a question, where first they will ask you to find the velocity and acceleration, particularly acceleration in the Eulerian and the Lagrangian form, starting with the deformation, starting with the equations of motion. And then they will ask you to use the material derivative and check that you get the same acceleration field. So please check it. If it's turning out to be different, then there's something wrong in the algebra. I hope that answers the question. Right. So let me move on. So this was the topic on deformation gradient, where we had the where we defined the displacement field, which is an extremely important quantity that we use when talking about deformations in continuum mechanics. So basically, displacement is the displacement of any material particle. Although the material quantity of interest is not displacement, but the differential displacement, as we'll see later, because we're talking about deformation, and translation is not of interest for us. Right. So displacement field again can be written in the Eulerian description or the Lagrangian description. It's just a geometrical quantity, which again can be expressed in any way. Now there was again a question here that I had discussed some sort of a motivation of the displacement field in the Eulerian description, where I said that it's a function of small x and p. So it's useful if you have you would want to know where particles at any given time are coming from, and you use the Lagrangian description where you are interested to find the displacements of the particles where they started from. But of course, this is just a motivation. I mean, of course, once you find the displacement, you can always track the particle back into the um, reference configuration, or you can track the particle in the spatial configuration using displacement. So all the information is there in any kind of expression. It's just that how we can readily use that expression for finding the quantity of interest. So if you're interested in what is happening to particles, then you would use a Lagrangian description. If you're interested in what's happening to points in space where you may have different particles at different times, you use the spatial or the Eulerian description. Then we discuss the deformation gradient tensor, which is your F tensor. That's this one. So we wrote dxi as f times d capital X, and this sort of is a very important quantity. It's a finite deformation gradient tensor, which tells us that if I give you f tensor at a given point, and then you would know what's happening around the point by writing d small x for any vector in terms of the d capital X. So basically, if you find any capital Q around a capital P, you can find where the capital Q has gone at a later time. Okay, relative to capital P, because remember, translations are lost, so it's only the um, relative positioning that's relevant. We also discussed F inverse, which is just the inverse of F if you want to write capital X in terms of small x. And then we said that F can be homogeneous or it can be non-homogeneous depending on whether the deformation depends on capital X or not. So homogeneous is where it does not depend on capital X. Any spatial point you see, the deformation does not depend on capital X. Of course, small x may depend on capital X, but when you take the derivative xi comma a, that is not dependent on capital X anymore. Right. So we discussed some scalar measures, which again help us understand the meaning of different terms in tensors, especially the strain tensors. So we took d small x squared minus d capital X squared, which is something you can measure. You can measure the change in the squares of lengths. And through that, we developed the idea of the Green's deformation tensor C, which again is a very important tensor when we talk about finite deformations. And then we talk about, then we discuss, then we express the Lagrangian finite strain tensor capital E as half of C minus identity. Again, this was done because ultimately we'll want to discuss the infinitesimal strain tensor later. Right, so we saw that C is symmetric, which again is a very important property, as we'll see later in the lectures on constitutive models. We briefly touch upon that, but this is important to express that C is a symmetric tensor. And then we wrote, um, then this is just the Eulerian description, where you have the Eulerian finite strain tensor small e. Then we talked about this was just one vector, but now we're talking about the relative change of two vectors. Because remember, deformation, we always have some sort of relative change in the angles as well between elements. So we talk about the dot product between two vectors, d small x1 and d small x2, originating from the same point P. It's basically what's happening to an element over time, or when it goes through a deformation. So here we saw that ultimately the conclusion was that if capital E is 0, because we're still developing the understanding of strain, if capital E actually is 0, then this, which is we call no strain, then what we have is we have pure rigid body rotation, in the sense that all lengths will remain the same for elements, and angles between any two elements will also remain the same, or any two vectors will remain the same. So if that is the case, then the only motion possible is translation and rigid body rotation. But translation is not interesting for us. So what we see is that it's a rigid body rotation. So this capital E, by that logic, is quantity which is isolated to measure the deformation and not rotation. So rotation is separately handled. E does not have any information about rigid body rotation. It has information about stretching and shearing, which is change in lengths and change in angles between elements, which we call deformation in general. And just as a motivational exercise, we showed that if a body is going through rigid body rotation, which we anyways know how to express through an orthogonal rotation tensor, then we see we just basically want to reconcile the ideas that we developed earlier about tensor transformations with this idea of rigid body rotation for a for a zero strain situation. So this is what we showed. We sort of showed both ways, right? We started with equal to 0. Um, we got rigid body rotation. We started with rotation. We got equal to 0. So this, let me see if there's any question that people had on this. Right. So then we went to infinitesimal deformation theory, which is extremely important. So there, here, what we said was that let's express our E, the Lagrangian finite strain tensor, in terms of displacement gradients. We tend to work with displacement gradients because whenever you, I mean, experimentally speaking, let's say whenever you measure things, you measure the change in positions of points when a deformation happens. So displacements are things that you can measure. So we talk in terms of displacements, not small x's or positions. So you will usually see that things are expressed in terms of displacements or the gradients. So we express the Lagrangian or the Eulerian finite strain tensors in terms of displacement gradients. And for infinitesimal deformation situations, we notice that these displacements or displacement gradients are small, uh, relatively speaking, to whatever you were comparing them against. So product of use or gradients of use are going to be much, much small. If you multiply a small quantity with a small quantity, you get a much smaller quantity. So then you can neglect the square terms with respect to the individual terms. So this sort of allows the linearization of the strain tensor. So here we saw that capital EAB is now expressed only in terms of UA comma B and UB comma. So there's no nonlinear term anymore. So mathematically things become simpler um, for this infinitesimal deformation situation as well. And we also see that small e and capital E, they boil down to the same quantity, which we call the epsilon tensor or the infinitesimal strain tensor, which through its definition is the symmetric part of the displacement gradient tensor. Right. So we again then showed that epsilon equal to 0. Well, we had already shown for E. So from the same logic, epsilon equal to 0 also denotes a pure rotation situation in the infinitesimal sense. And then we use the scalar measures that we had discussed earlier to understand the different terms in the epsilon tensor. So the diagonal terms are uh, the ENs, the longitudinal strains in the coordinate directions, and the off diagonal terms are the angle changes between perpendicular elements of the material coordinate system. Right. So then there's a question. I mean, you can type it and then we'll discuss it. So for infinitesimal strain tensor, I'll move on from here. And then we also showed that um, if you're dealing with the principal directions, then what we see is that there's no change in angle between principal direction. The principal directions are perpendicular, we know that. A cuboid uh, oriented along the principal axis will remain a cuboid, although it may change the lengths. And this idea of the diagonal terms in epsilon star, denoting the longitudinal strains, helps us express the um, volumetric strain as the first invariant of epsilon. Again, a very important idea to know about. So this sort of completed the discussion on strains, and then we had a tutorial. We didn't have much of a query here. Right, so in rotations, there were some questions. I'll stop and discuss. In fact, this lecture had lots and lots of questions. So I'll discuss a few. So we said that U displacement gradient tensor can be written as a sum of a symmetric and a skew symmetric. That's from the mathematical sense. A symmetric was epsilon, that's the infinitesimal strain tensor. The skew symmetric part is omega, which we call the infinitesimal rotation tensor. Now remember, it's the infinitesimal rotation tensor, right? So there was some confusion later with the finite rotation, so I'll try to clarify that. Skew symmetric tensor is a tensor where the diagonal terms are zeros. So we only have three unique values. So intuitively, we can define an actual vector associated with that. Uh, it's the omega vector, uh, dual vector of omega tensor. And this is the vector around which the rotation is happening. Then we defined the idea of stretch ratios, where there was a question on this topic where capital lambda and small lambda, there was a question. So, I mean, both of them are stretch ratios, which is defined as the ratio of the length of the element in the deformed configuration. That's d small x to the element length uh, in the reference configuration, which is d capital X. Except that small lambda is when you're tracking for a small n hat. So, in the sense that we give you where the element is oriented later, and then you find the stretch ratio for that. And capital lambda, we give you where the element was oriented in the beginning, capital N hat, and then we give the stretch ratio for that. So we could have used the same symbol by just changing the subscript from capital N hat to small n hat, but usually we have vectors which have coordinates. It's confusing if I put in the vector coordinates in the brackets. So if it's capital lambda, then the vector will mean the vector in the reference configuration. And if it's small lambda, then the vector will mean the vector in the spatial coordinate. So same definitions, except that just where the uh, vector is coming from. There's a question that we promised that we'll show the omega vector in tutorial, but we just used it. Okay. So I think the question is how we get the. If we go back, so I think your question is that if we have an omega tensor given to us, how do we get the omega vector from that? Right? Is that the question? Uh, I think we would have shown it somewhere. I'll make a note of it. If not, then we will share that. It's a we'll have a look. Maybe this was discussed at a later stage somewhere else. Okay, I'll check. I'll check and get back on this. I've noted that down. Right. Then we talked about. I'll come back to the question. Let me finish this discussion on finite rotations because we do have a couple of questions. I would want to discuss that first. Then I can come back to the question. So finite rotations. On the right hand side, we said that we have multiplicative or polar decomposition when we talk about finite rotations. In infinitesimal case, we do the additive decomposition into a symmetric and skew symmetric. So in polar decomposition, we write the I mean, r times u or v times r. Basically, depends on whether you take the rotation first and then the stretch, or the stretch first and then the rotation. So rotation, this matrix is an orthogonal matrix, and the stretch tensor is matrix is symmetric tensor. So I think the procedure was straightforward, but the confusion happened when we showed from finite to infinitesimal. So let me see where the question was. Um, so one of the questions was that how do you actually see that you are getting the I mean, the easiest thing to do is that you have f is r times u. So what we do is we develop the expression for u, which we have here. So u is delta plus half of epsilon, and then r from here is delta plus half of omega. Sorry, delta plus omega, and this was delta plus epsilon. And when you substitute that into your f here as r times u, then what we'll get is we will get, when you multiply these, you get an identity plus epsilon plus omega plus a product. Now the product, if you expand, will have products of displacement gradients. So ui is multiplied by ui comma c multiplied by another derivative of displacement gradient element, and then that becomes much smaller. So those products of epsilon and omega can be neglected in relation to epsilon and omega, and this is an f that we're talking about. But since we want to compare with the displacement gradients here, so displacement gradients are f minus a delta, so you can take the identity on the other side, and you will see that this multiplicative uh, polar decomposition, which was a product of r and u, essentially becomes a sum of epsilon and omega. So this is something we didn't do it, but I think it's a good exercise to try it out, and you will indeed see once you substitute this r in. Now the other confusion was that in the lecture I mentioned uh, very hand wavily that this u minus delta is like an f minus I. It is not equal to f minus I. What I meant was that if you see here, and again this confusion occurs in many cases, that sometimes we have an f, sometimes we have a ui comma j. Now the difference between them is one is coming from deformation, the other is displacement. So you have to subtract an identity from the deformation gradient tensor to get a displacement gradient tensor. So that's what I meant by saying that this u minus delta is like an f minus I. So so u is not this capital U is not like a displacement gradient. You have to subtract an identity from it to get a quantity which is similar to displacement gradient. But if that confuses you, then you can simply use u and r in the expression for the f, and then you can derive small u a comma b from that. Right. So one other confusion that occurs in many cases is the confusion that um, the rotation. I think that was a question as well. That the tensor here, omega, which denotes rotation, is skew symmetric. So does that mean that capital R is also skew symmetric? And the answer is no, because R is finite. Firstly, we don't talk about. I mean, if R was the only thing happening, there was no U, so that will be F will be equal to R. So to compare them, we have to subtract an identity from that, of course. But even then, it may not turn out to be skew symmetric because R is in general a finite rotation. Now, if you take the case for a limiting case for infinitesimal rotation, now we're talking about rotation only cases for isolation of rotations, then under the infinitesimal uh, approximation, yes, your R will become skew symmetric, but for a finite case, R will not be skew symmetric. So there was a problem actually where I think it was lecture number 45. Let me show that. Right. So here we had a problem where, yeah, problem number two, we had to find the matrix representation of the rotation tensor R. Let me show you rotation tensor, which is this one. So we can see that it is not skew symmetric. So this is not the omega tensor because it's a finite deformation. Now, just to impress upon a fact that under infinitesimal assumption, now this is not an infinitesimal situation, so we can't do anything here. But let's see if I can give you an example, because this confusion appears in many situations. So I thought of clarifying that. Okay, it was your question. Okay, let's see if we can write something here. So if we have a situation, let's say, where it won't be a very neat writing. So small x1 is capital X1 times cosine of theta minus capital X2 times sine of theta, right? And it's a 2D situation. And then your small x2 is capital X1 sine of theta plus capital X2 times the cosine of theta. So this was the motion that we had. So if I calculated the F tensor, that would turn out to be um, x small x1 del small x1 upon del capital X1. So that's a cos theta. Then we have del small x1 upon del capital X2. That will be a minus sine theta. And then similarly, we'll have a sine theta and a cos theta. Right. Now you can easily see it's a rotation. I mean, the motion happening here is a pure rigid body rotation. It's rotating body with an angle theta about the x3 axis. It's a rigid body rotation. You can easily check that in this case. And this is an F we are talking about. So if we want to find the U, that's the tensor U I comma A, then that will turn out to be F minus identity. So which becomes a cos theta minus 1, and then we have a minus sine theta, and then we have a sine theta and a cos theta minus 1. The question is this skew symmetric? And the answer is no. We can easily see it's not skew symmetric. So the displacement gradient here is not a purely skew symmetric, although it's a pure rotation situation. But if we take the situation of infinitesimal motion here, deformation, so that means the theta is extremely small. So if that happens, then what we see is that cos theta minus 1 will approximately be equal to 0, because for theta being very small, cos theta is approximately equal to 1. And this cos theta minus 1 again becomes a 0. And for very small angles theta, sine theta is approximately equal to theta. So we get a. So now this matrix 0, minus theta and 0, that is skew symmetric. Right? So what we see is that under the infinitesimal deformation situation, your uh, rotations, I mean, when you take identity out of it, then it becomes a skew symmetric tensor. So please don't confuse yourself with the fact that finite rotations do not satisfy the criteria of skew symmetry. It's the infinitesimal rotation, but you have to also have to subtract an I from it because of the way we define the tensors in the two situations. I hope that clarifies, because that can actually be quite confusing at times. Right. Right. The other question which confused people, I'll quickly jump to that. We're getting out of time now. Is on compatibility. So let's see if we can. Right. Let's actually go to the lecture where we discussed it. Is it lecture number 41? Yeah. So in lecture 41, we discussed the idea of compatibility. So one question was that the first fundamental question was that we motivated the need of a compatibility with the fact that we have. Sorry, I have to reshare my screen. Right. Yeah. So we motivated the need of compatibility with the fact that we have six differential equations where we are solving for the unique displacement field given the epsilon tensor, which has six unique components. And then we said that we have only three unknowns. So this sort of motivates the need for um, extra equations. And then we came up with six compatibility equations. The question was that now this becomes an undetermined system, right? Actually, it's not the case because the equations of compatibility are have dependency in them as well. Now, if I go to this situation where we started with the curl of epsilon, um, this is what gives us the compatibility. Okay, I'll discuss why we use this. But the question is that if you take a divergence of this, that becomes a zero. Divergence of the curl of a quantity is identically zero. So what that will tell us is that the quantities of curl of epsilon are also related to each other. So the six equations of compatibility are not unique. There's some linear dependency under the derivatives as well. So that is sort of reasoning for that. And the other question was that why do we start with the curl of epsilon? Because we want some sort of relationship between the elements of epsilon under their derivatives. So we look for an operation that results in a zero on the right hand side, so that now we can get some relationship. So again, it's not trivial. Saint Venant came up with the compatibility equation, although not in this vector calculus form, because vector calculus came later. But it's coming up with this idea is not trivial. So, but still, it's an interesting idea that we need a zero on the right hand side with some vector operation on the tensor operation on the left hand side, so that we can relate the quantities using that. Right. Right. So this kind of again the same idea for the curl of f equal to zero as well. If you take that, you take the divergence of curl of f, that is zero. So that would mean that the compatibility equations you get for the finite case will have some dependency on them. So they're not all independent conditions. So I will check again that getting omega vector from omega tensor, if we can show that. I remember we had included in some lecture. I'll try to look for that, and maybe in a later lecture we showed that. tutorial problem. So we will direct you to that. If not, then over the chat we will share the derivation for that. Okay. So is there any other question? Otherwise, we will close this. Although we plan to have balance laws and in this lecture as well, but we thought of including only kinematics because that's a topic that requires a lot of discussion. And then the balance laws will be handled in the next week's discussion. We will discuss balance laws along with uh, the remaining parts. Yeah, so I mean, under the so the question is that does that mean there are only three independent equations in compatibility? So under the derivative form, yes, they're not only or linearly dependent. So if you um, take one, then you can use the others. So you'll need three in an independent sense for that. But again, there's derivatives there, so one has to be careful with that. There was one other question. Unit vector of infinitesimal omega vector is a direction of the axis of rotation. Yeah, so the whole meaning of omega vector is that the rotation is happening around the vector. So that is the axis of rotation. Yeah, so you're correct there. That's a definition of the rotation vector. So we will. I'll address all the questions on balance laws, and we will answer any questions if you have on balance laws next week. So we'll try to keep it focused around balance laws because constitutive modeling is just we gave a flavor of constitutive modeling in this course. So we don't want to get too deep into constitutive models, but balance laws is something that we do want to do rigorously in this course. So we'll focus rigorously on that. So any questions on the chat group, we will address that and make a note for the discussion next week. So I think it's time we'll close this session now. So thank you very much, and I'll see you next week.